Thank you to the organizers for inviting me. Yeah, I'm Yanpei. Today I'm going to talk about a fundamental bottleneck we face in 3D generative AI, and sorry, yeah, and how our work to solve it provides a new and scalable foundation for creating the content that powers applications like digital twins. Um, Before we discuss the problem, let's see some state-of-the-art in generating like a single shape. Generative AI can now create 3D shapes with stunning geometry detail from single inputs. And the objective here is pretty straightforward. We aim like efficiency and fidelity. We need a 3D shape model that's high resolution, but also scalable so we can train it effectively. And here, our highlight model here is like the triple SF, which was designed to handle arbitrary topology and capture unprecedented detail. And it's our paper at this ICCV. And the core design here is a representation we call sparse flex. It allows us to generate meshes at extreme high resolution and crucially with arbitrary topology, meaning that we can handle the scene structures, holes, and complex surface common in mechanical parts. But in solving the geometry problem, we also revealed a deeper one. The output of all these performing models is what we call a digital statue. And in fact, what you see here is an evolution of our own model, our own image 3D models from V.4 to our latest V3. And as you can see, the quality has improved dramatically. The geometry fidelity and the accuracy of the structure and the expression of the fine details are now at the level we could only dream of like a couple of years ago. Fantastic, and this is a huge but, they are fundamentally dead objects for practical use. Think of gaming, simulation, industrial design, and professional pipeline. These beautiful high fidelity meshes are often unusable as they come out of the generator. Why? Because they lack three critical components. First, they lack the explicit structure. It's a single monolithic mesh that doesn't understand its own parts, which makes granular editing almost impossible. You can't edit the wheels of a car or has the hinge of a door because the model simply doesn't have a concept of like what wheels or doors are. And second big lack, they don't have a rig. They don't have the internal skeleton, the control system you need for posing or articulation. And third, which follows directly from that, they lack motion. You can't animate them easily because the underlying generation architecture just doesn't provide those hooks which are needed for dynamics. And this brings us to what we're discussing today. This digital statue problem we face is, I believe, a mirror of the content bottleneck people also face in the world of like digital twins. Whether for creating creative assets in gaming or simulation assets for engineering, the fundamental challenge is the same. The slow and manual and expensive creation of assets that are first composable, which means they're made of distinct and editable parts, and second, articulation, which means they are ready for motion and interaction. Also, how do we solve this? Our solution is generative pipeline design from the ground up with a fundamental different goal. The goal is not to create a single monolithic shape. The goal is now to create a dynamic assembly. And to do this, our pipeline first generates a structural layout, which serves as a blueprint defining the object's parts and their relationships. And then it generates the high fidelity geometry for each component based on that plan. Finally, it defines the kinematic structure, which specifies how the parts can move relative to each other. And in the following, I will show you how each stage works. And so this vision of building a future of interactive user-generated 3D let us fund triple. And we are a team dedicated to build a new generation of 3D tooling and application from the ground up, and specifically designed to leverage these modern like AI capabilities. And our focus is on simplifying 3D creation through AI, which with an emphasis on assets and platforms optimized for real-time interactive environments. And our vision is a future fueled by interactive and user-generated 3D. And we are not building this alone. We are fortunate to collaborate with a diverse group of partners. And this collaboration is key to building a platform that truly serves the creative community. And the core of making a composable assets is to think about its structure first. And this is the whole process follows a three-part logic: deconstruct, generate, and assemble. And let's kick off the deconstruct stage. This is followed by it's powered by Holopart, that stands for Generative 3D model segmentation. So when you look at a 3D scan or generated 3D shape, deconstructed into meaningful parts isn't just about segmenting the visible surface patches. That's standard segmentation. But the real trick is inferring the occluded geometry that with the hidden parts. It's the A-model segmentation, and it's essentially trying to see through the object. And Holopart uses a diffusion-based model designed specifically for this 3D part shapes completion task. It starts by leveraging a strong generative prior learned from massive data sets of general 3D shapes. So the model knows what things generally look like. Then to make sure the completion is both geometrically detailed and globally plausible, the model uses two attention mechanisms. First, the local attention. This captures the fine-grained geometric details needed for the specific part you're looking at. And the second, global shape context attention, which uses information from the entire object to ensure the new parts make sense within the whole structure. And the result, you can get the part-ware deconstruction that's generally semantic. It understands the components, so it means you can separate individual parts and edit them. Pretty cool. Again, next up is the generate stage, and this uses Omnipart. And Omnipart is designed to make sure generations are modular and structured right from the start, like from scratch. And Omnipart operates in two main stages, and they are controllable. The first stage plans the abstract structural layout of the object parts, like planning the bounding boxes and their relationships. Those bounding boxes just forms the scaffold. It does this autoregressively, and you can optionally get it with 2D input masks if you want more control. And the second stage is spatially conditioned part synthesis, where the actual high fidelity geometry of each individual part gets synthesized based on the scaffold. And this ensures the final object is modular by design. And using Omnipart, you can generate a wide range of complex and modular assets with coherent structure and semantics from right from the start. So users can now edit parts directly and change the structure through masks or even mix and match components. Then this moves us from static to truly modular and controllable creation workflow. And this finally brings us to the part of composition, the assemble. If Holoparts let us deconstruct and Omniparts let us generate modular parts, we then need a robust way to put them all together. This is the role of assembler. Given a set of 3D parts and a reference image, how can we assemble them automatically? And our assembly module or model introduces two key designs. First, to make the assembly more robust, we predict a holistic set of anchor points rather than those brittle SE3 poses. And secondly, we frame assembly as a generative path using diffusion model, which naturally handles ambiguities like symmetric parts. And the model architecture uses this dual conditioning. It takes the shape features from the individual part meshes as well as the guidance feature from the reference image. So diffusion transformer then uses both of these conditions to intelligently generate the final anchor points required by the assembly. And this approach is designed to be highly scalable, which can handle a large and variable number of input parts for complex objects, which means you can basically assemble the same set of parts to different shapes according to the reference image. And like bringing these concepts together unlocks a new workflow. Let's say like deconstruct, generate, and assemble. Imagine an LLM today looks at an input image, decomposes into a semantic list of parts. Then a standard image to 3D model generates those individual parts, and finally the assembler can intelligently put them all together into a complex and say scalable 3D assets. Then this shifts the 3D creation away from just generating one big monolithic thing towards the semantic compositional design. It's just a different way of thinking. Right. To further prove this compositional approach can handle strict and rule-based systems, we apply it to the world of Lego. And our Lego ACE engine is to build to demonstrate this principle. It doesn't just create let's say a cloud of bricks. It understands connectivity, stability, and procedural building steps. This ability to generate assembles that adhere to a physical or logical constraints is absolutely critical for creating valid and useful digital twins, or like digital twins of mechanical or architectural systems. Here we show the kind of expressive and complex assemblies we are achieving, like the models with both semantic meaning and structural integrity. So the challenge in LEGO generation actually mirrors many like real-world engineering problems. You start with a library of standard parts, which are here are the bricks, and you have a set of instructions of a high-level goal. And the objective here is to create a semantic, meaningful, and physical plausible assembly. And automating this process is incredibly difficult. Yeah. So our research question becomes, how can we build a generative model that bridges this gap? And how can we take a library of discrete parts as input and learn the procedure logic and assembly to to create valid and complex structures? Previous approaches have been severely limited by data. They often rely on small and manually annotated data sets where each single connection between the bricks is explicitly labeled. And this actually incredible labor-intensive process will restrict the diversity of bricks and complexity of the models. So these approaches simply doesn't scale. Okay. And to solve this scalability problem, our first step was to build a proper data foundation. We curate a massive data of over 9,300 unique Lego bricks, Lego brick types, far beyond the few, like say, dozens used in previous work. And this library is comprehensive. It covers everything from the most common bricks to a very long tail of specialized, rare parts. Including this diversity is crucial for generating truly expressive and realistic models. And using this library, we then build the LEGOverse dataset, the largest of its kind, with over 55,000 unique assemblies. And this is the largest dataset that's this is a large-scale dataset that is absolutely necessary to train a powerful foundation model for this complex LEGO assembly task. And the models in, let's say the assets in LEGOverse span a huge range of complexity from, simple builds with a few dozen bricks to those complex constructions with even hundreds. This actually ensures our model learns from wide variety of structural patterns. And with the data in place, we then develop the model. We call it LEGOverse, Lego ACE. It's an autoregressive decoder-only transformer. And the key idea is to treat the building of a, say, Lego model like writing a sentence or a paragraph. Each brick with its 3D position, rotation, and unique type is then converted into a sequence of discrete tokens. The entire assembly becomes a single and ordered sequence. Then the model learns to predict the very next brick in the sequence, conditioned on all the bricks that have been placed before it. By doing this over and over, it implicitly learns the rules of connectivity and structure stability without ever needing explicit connection annotations. This is what allows us to scale our dataset. So what can the model do? Here are the results conditioned on multi-view normal maps. This is analogous to giving a model a 3D schematic and asking it to reconstruct using valid Lego bricks, which it does very, very effectively. It can also be conditioned on text. Here you can see it generates diverse assemblies from natural language descriptions, like, for example, a space shape with a large angled wings. And this demonstrates a deeper and semantic understanding of the relationship between language and 3D structure. Then, when compared to previous unconditional methods, the improvements in structural integrity is clear. And our approach by learning implicitly from a larger and more diverse dataset consistently produces plausible geometry and avoiding the intersections and disconnected parts that plague other methods. And we also compare LEGOverse to general image to 3D models. While those models can capture the overall shape, they produce a mesh. Then when you try to, say, Legolize those meshes, you lose all the structural integrity and resulting this disconnected mess. And Lego ACE, on the other hand, generates a valid and buildable assembly directly from the image. Thus can faithfully follow the input while respecting the physical constraints or the constraints learned from the data of the Lego system. And of course, the ultimate test of validity is, of course, can you actually build this? And the answer, of course, is yes. The sequential output of our model can be as a step-by-step instruction to construct the physical stable models in the real world. And this demonstrates a true and grounded understanding of the procedure generation and physical constraints. Okay. Of course, a digital twin doesn't just exist. It moves and functions. And manually defining the movement or the motion via rigging is a massive bottleneck. And we now have to move to the arguably the most complex challenge, installing the control system or the rig and enabling the dynamic motion and bring these assets to life. Just think about the sheer diversity of 3D assets in any motion, any modern game or film. You got humanoids, obviously, but also like four-legged animals, birds, fish, spaceship, or like even mechanical assemblies. Traditional rigging often needs to like specialize algorithm different approaches for each class of the object. And here our new method we call Unirig aims to provide a unified framework, automated method that can handle diverse skeleton rigging for any shape. So, moving way beyond just like standard humanoids. And it's built on dataset we collect called the Rig Excel dataset. And this dataset covers the massive range of topologies and rigging schemes. Then how does it predict the rig? Well, the core is an autoregressive rigging predicting process. You can, think of it like a skeleton tree GPT. Let's see a quick demo of the unirigging action. You can see Unirig automatically generates skeletons for diverse shapes like animals, birds, fish, and of course characters using the autoregressive approach. It also predicts skin weights, allowing those generated rigs can be directly used for smooth and fluid animations. Yeah. Okay, so once Unirig has automatically rigged out our asset, it needs to be moved. The asset needs to move, right? And this is the domain of our method Animax. And Animax generates 3D animations from the mesh driven by a textual description of the motion. And traditional motion generation methods usually relies on motion capture datasets, which almost always use like a fixed skeleton system, typically just captured bipedal, humanoids. So those methods struggle massively when they are, faced with the diverse arbitrary topology, coming out of the generative systems. And the core system in Animax is a multi-view video post diffusion model. The model is trained to simultaneously denoise two things for a given action. First, it generates a sequence of multi-view video frames showing that action, like generating videos from different angles. And second, the corresponding sequence of 2D joints for that exact same action. So this joint training provides critical complementary grounding. It gets information from both domains. For example, the 2D video frames are, video frames are adapted from powerful pre-trained video diffusion models. So they can supply the grounding in realistic appearance and plausible dynamics. And meanwhile, the simultaneously generated 2D poses, which is actually the explicit structure data, it then can prevent the asset from doing crazy, impossible things like collapsing on itself or twisting into something a bizarre configuration. So at inference time, this is the result that the Animax method can finally get for us. Yeah. So finally, these principles of composition need or must scale. So this focus on placing these fully articulated components into a compositional 3D environment, which is the scene. And this is where our MIDI project comes in. Here MIDI stands for multi-instance diffusion for like single image to 3D scene generation. This allows a simultaneous generation of multiple instances all at once. And these objects are, effectively created together with inherent knowledge of each other, the other parts, presence and position during the generation process within itself. So different from retrieval or like multi-stage pipelines, this attention mechanism fundamentally removes the need for those complex, often like error-prone post-generation layout optimization stages or like separate retrieval methods. And this workflow allows us to go from a single image, generate a 3D shape and layout, and use those texture models to generate a complete and textured 3D scene containing multiple objects. So let's put it all together. We've built an end-to-end generative engine that, or generative pipeline that, starts with a simple and accessible input like a single image. And the pipeline automatically generates a compositional, structure and, creates the geometry for each other, infers the kinematic rig and articulation, and finally brings the entire assembly to life with, controllable animation. And as shown here, this entire stack isn't just, research papers. It's actually being materialized in applications right now. And it's our product called Triple Studio, which is web application are immediately deploying the research. And in this transforms the weeks-long manual effort of a team or a team of artists into a single AI assistant interactive flow. And we strongly believe that sharing research drives, innovation. That's why we are open source the key components of our work, including many of the models mentioned today. And of course, the road ahead. So I think the next focus is on consolidation, which means the big vision is to moving from the pipelines of discrete and specialized models to a single or universal foundation model for creating digital twin. First, like achieving a unified model architecture. Maybe imagine like a single multi-model that holistically understands geometry, appearance, and motion all at once, and intrinsically, rather than linking together several, specialized modules. And second, of course, ensuring the zero-shot generalization across all domains is those foundation models should do. And third, I think agentic and interactive workflows are the next steps, and which means moving beyond simple, like say, one-shot generation, and moving towards a collaborative and stateful AI agent, something that can assist in the iteration design process. So because, black box and one-shot generation isn't just suitable for creative or engineering tasks. And we are building we should build a, interactive and collaborative, systems where a stateful AI assistant can work with the artist or an engineer. So yeah, this will allows your experts to use their knowledge to guide and refine and validate the assets or the 3D models that they are being created or processed. Okay, with that, happy to like answer any questions.